Welcome back to the Office Hours with Dr. Clark. So, we want to talk today about acids and bases. So, there are a couple definitions from acids. So, you have the Bronsted definition. Acid is a proton donor. A base is a proton acceptor. Do you think of like HCl? HCl, water is actually can be an acid or a base. You think of vinegar. So Lewis definition of acid and bases. Acid is an electron pair acceptor, and a base is an electron pair donor. So, so if we think about Gen Chem, we think of H plus, OH minus, H plus are acid, OH minus are base, and we form H2O. Right? AQ, we get a liquid. All right, it's our classic acid base conversation. Now, pKa is a measure of acidity, right? And that takes into account how much hydronium is formed. If you think about the classic equation here, you have H3O plus A minus. So Ka is we call the acid equilibrium constant. It's the concentration of your hydronium times your conjugate base over the concentration of the acid. So if we have a strong acid, you're going to have a lot of hydronium. So your Ka will increase with increasing hydronium. So that's a strong acid. For weak acid, your Ka is going to decrease because you're going to have more of the parent acid and less of the hydronium. In other words, this denominator is going to be stronger, bigger with a weaker acid, and the numerator is going to be bigger with a stronger acid. So pKa is the minus log of the Ka. So it gives us some, numbers to work with. Because Ka, you can see sometimes you have like 1 times 10 to the minus 7 or minus 8, and nobody wants to deal with those values. So pKa gives us numbers like minus 9 to 60, right? So as pKa goes up, acid strength decreases. Right? So in organic chemistry, we use pKa. We can use Ka, but we use pKa because it gives us like some nice numbers, like 6 or 4, 15.5 to work with. So immediately in organic chemistry, we like to think of position of equilibrium, right? Position of equilibrium. So reaction favors production of weaker, in other words, more stable. So in organic chemistry, weak means stable, less reactive. So for example, if I'm looking at this reaction between, let's say, here I have, this is an alkyne, pKa is around 20, 26, and I have hydroxide. And then my potential products for this reaction is the conjugate base of the alkyne plus H2O. Right? So if you think of, so we're looking, so let's put our lone pairs in. Lone pairs on the water. So, and actually, I'm gonna draw the H's on water, and we're gonna see later why I did that. So, the pK of water is pK is around 15.7. So, according to acid-base theory, the reaction is going to go towards the weaker acid or the more stable acid. So the weaker acid is going to be the one with the higher pKa, which is this case is 26, which is my alkyne. So I'm going to draw my arrow like this. The longer stem is going to go to the left towards the weaker acid. So we say the position of equilibrium is to the left, meaning the reverse reaction dominates. Okay. And therefore, so here's a lone pair. So we start on the lone pair, we grab the H, and then the pair, now the single bond between the H and the O breaks and becomes a lone pair of the O. And that's how we form our hydroxide um, and our acetylene. So that's how we do position of equilibrium. Now, we can look at acids and bases different ways, like a qualitative um, way to judge acidity. Now we have to go to the lab to measure, pKa, things like that. But we can look at, we call it REO. A means atom, R is resonance, I induction, and O orbital. Let's do some comparisons. So if we're looking at, say, let's look at an atom. So atom, we're dealing with more electronegative atoms stabilize charges. And when I say charges, I mean negative charges. stabilize negative charge better. So for example, if I'm comparing, so this is an amine, you know, related to ammonia. And if I'm comparing that to ethanol, this is an example of an alcohol. So these are my acids. So this is ethanol. So if I form the conjugate base, it's going to be a negative charge on the nitrogen, and then it's going to be a negative charge on the oxygen. So which conjugate base is more stable? It's going to be, what do you think? Question is, which atom is more electronegative? So this oxygen is more electronegative, thus more stable conjugate base. So therefore, this acid is more acidic. And the pKa will reveal that to us. pKa is around 16, pKa for this is around 33. So clear difference in acidity. Let's talk about resonance. So let's look at phenol. And I'm going to compare that to ethanol again. With pKa around 10, pKa 16. So conjugate base, you got to make sure you learn, how to identify the acidic hydrogen. Sometimes, we'll tell you, and other times, based on having, learning, these rules, you gotta be able to pick out a conjugate, excuse me, the proton that's going to be acidic, because not all protons in organic chemistry are acidic. And we're going to do a couple examples of that. So, so I'm comparing these, and they're both on an oxygen, so I can't say, okay, one is more electronegative than another. But from our experience with resonance, I could see that this oxygen is allylic because it's connected to a double bond via a single bond, and we can form resonance structures. And we can actually form a few. Whereas with ethoxide, which is what this is, no resonance. So my negative charge on the phenoxide ion can be delocalized, meaning it can be stabilized, whereas there's no stabilization here. That's why this acid, this proton here is more acidic than this proton. Because once it leaves, the conjugate base is not very stable, so it doesn't really want to leave. Whereas this one is okay leaving because it has a stable conjugate base. So that's resonance. Let's look at induction. So with induction, I'm not looking at resonance or the type of atom in a sense. I'm looking at what else is on my molecule that can help stabilize my charge. So if I compare these two, so let's call this A, let's call this B. pKa of A is less than pKa of B. The reason being, when I form my conjugate base, this chlorine being electronegative is pull electron density and spreading out the negative charge even better. So not only does it have resonance, what they both have, right? But now I have an additional stabilization feature, and that's going to make this more stable, thus this more acidic. And say I added more chlorines on there. I had chlorine here, another chlorine there. It would even become more acidic because I have more opportunities to delocalize the charge. And then the last one thing is orbital. So if I'm looking at, again, let's take an alkyne. I'm looking at an alkene and an alkane. So I have an sp hybridization here, sp2, sp3. This is so my pKa decreases in the direction of the alkyne. The more S character in an orbital, the more stabilizes a negative charge. So if we look at SP, this 50% S is only, ratio of 1 to 1. This one is about 33% S. And then this one is about 25% S. So the s orbital is the closest to the nucleus. So if a charge is in an orbital that has a lot of s character, it's going to be the closest to the nucleus and thus more stabilized. So those are the 4 different ways to judge acidity in a qualitative way. Right? We can't really know for sure if an acid is strong or weak until we go to the lab and do some experiments. But something else I wanted to talk about, which can kind of throw off the Arrio rule, is size. If I compare H2S to H2O, I see something weird because sulfur is electronegativity is about 2.6, oxygen is 2.5, so 2.6, 3.5, excuse me. So the conjugate base should be less stable than the conjugate base of water, which is hydroxide. However, we find that the pKa for H2S is around 10, pKa of water is around 15.7. So clearly H2S is more acidic. The reason being, sulfur is bigger. Better at stabilizing. So bigger atoms can spread the charge around better than smaller atoms can. Okay? That's why HCl is more acidic than HF. If you compare these two, HCl, HF, even though HF is more, fluorine is more electronegative, chlorine is 3, fluorine is 4. Well, chlorine is a bigger atom. So if you go down the group and periodic table, you'll find that as you go down, the acids become more acidic, even though the atoms themselves are becoming less electronegative. So that's one way where electronegative part of Arrio can be trumped, in a sense, by size. All right. Well, so we looked at the different ways to qualify acidity, qualitatively. We also looked at So we looked at resonance, induction, the orbital, the type of atom. We also looked at position of equilibrium, and we started doing, looking at our curved arrows, and we looked at how pKa can indicate acid strength and exactly where do we get the concept of pKa from. So we talked about Ka, and we talked about the Bronson and Lewis definition of acids and bases. So join me next time, Office Hours with Mr. Clark.